Hello. In this video, I will talk about methods to discretize a transient problem. Means we have a physical situation where the process is evolving over time, and we want to simulate this, which means we have to calculate our physical variables at different time steps. And how you can determine those time steps and how you can relate those time steps to each other, what I summarize in this term temporal discretization, to get the parallel approach to spatial discretization, which we had in the last video. Also, this week, in connection to this temporal discretization, we will talk about stability concerns and properties of numerical models in general, not just stability, but also accuracy, boundedness, convergence, and consistency. So a couple of other, new vocabulary that is related with describing also the quality in some way of the numerical model. So the discretization of time is straightforward when you know how to discretize space. Because we are facing the same problem. So time as is space is continuous, right? So we don't have a snapshot where we, in our physical life go like, well, okay, this was this second and this was that second, but it's continuous, right? It's not stop motion, if you want to say so. And the discretization that you usually use for modeling forward or in general transient problems is based on finite differences. So we're looking here at the time derivative, which is simply approximated in finite differences. So we're taking the future time step t plus dt. So tt is just simply some difference from the time right now. So from the time t, we're adding something on top of it, whatever it is. So you're generating the gradient from a future time step minus the actual time step divided by the size of the time step. And so this is a point in time in the future, this is our current time, and the difference between both in time is dt, and then depending on the state of your variable. Right? So this is just approximating first order the time derivative by the difference and then divided by the time step size. How do you determine such kind of time step? So it is simply the difference between 2 points in time. So if I take yesterday and I take today, then the difference would be 24 hours. Well, you can express it. I mean, it doesn't matter about the physical units. You can express it in hours, seconds, days, years, million years, whatever you like. That's not the point. And the point is here that you're choosing your time step depending on the process you want to look at. Now, if we want to describe maybe atmosphere temperature, then an hourly or maybe 5 minutes resolution would be okay. So I want to have my simulation maybe on that kind of time scale. If I want to resolve it on that fine. Yeah. If I don't know, when I'm all climate change in the next 100 years, I will probably choose the coarser resolution because my process is not happening on a 5-minute scale, but happening on decades of years. But also, while your dt not just depends on the physics you want to look at, but also on a lot of technical issues of your numerical model. So, for example, your spatial discretization. As finer you discretize your domain, as usually as smaller, you also have to choose your time step, because usually processes happen quicker in a smaller space, right? So if you consider something like diffusion or so, if you look at 100-meter scale, a trace concentration will develop more slowly than if you look at like in a meter distance. All right. Then we have also connected with those ones, because spatial discretization time step are linked by stability. Your stability of the numerical method you're choosing will determine also will have an influence on the maximum possible time step of your numerical simulation to keep the simulation stable. Also accuracy, it kind of depends also with the physical processes again. So and your numerical method, of course, because of course you as finer you look at the process, so in smaller time steps, your accuracy is increasing. Why? Because if you remember, you're using some kind of discretization scheme, and maybe it's linear first order. And this is, of course, valid usually as smaller your time step is, because you're linearizing only about a very smaller time frame, and then for the next time frame you can change your inclination of your linear approximation, for example. And then also, of course, the numerical method itself, the solution process, and so on will determine your time step, or the maximum time step. Again, it's a maximum time step to achieve stability and accuracy. So we're separating here in this very, very basic course two ways of time stepping, and this is explicit and implicit time stepping. The idea of an explicit time stepping is that all the information that I need to calculate my future position is already known here. So going back to my groundwater example, I want to estimate outflow in the future. I say, okay, I'm looking at my current outflow, maybe on bit what is upstream, what is downstream, and then I can compute the time step of tomorrow. Right, so this is what symbolized here is. So this is t plus dt. So this is my future time step, which I want to compute at a position of x, of course, at some fixed position. And what I need to calculate this point could be, depending on your numerical scheme, knowing my value upstream and my current value, and maybe also some value downstream, and then I could compute the future time step. This is an explicit time step. So let's do this for an example of 1D groundwater flow. So we have storativity, we have transmissivity, and we have the change of the hydraulic head at some position. And I will just use finite differences here to keep things as simple as possible. So what we do is we approximate the time derivative as I had it on a couple of slides before. So we say, okay, we want to compute the hydraulic head at a future time step. We know it at the current time step, and those ones are separated by time step dt. On the right hand side, I use some spatial discretization scheme, centered in space it's called. We introduced it in the last video. It pretty much says on the video on the slide before here, so I'm taking the value upstream, the value downstream, and set it in correlation to my current position. So there is some weighting going on here. And now I can formulate this one just by simple, algebra, putting the s and the dt on the right hand side, adding this one so that I have also on the right hand side. And then I get an expression on the left hand side. So this is my unknown. And everything that's written on the right hand side is known because it's all to my current time step t. So all of this is known, right? And only have one unknown. The implicit time step is different to this because it doesn't only require my current position. Of course, this is always needed. I need my current variable value, but it sets the future time step value in relation to its neighboring points in the future. So I'm trying to find a consistent formulation in the future, which is consistent in itself, but which means I have a lot of linked unknowns, right? Because now I'm doing this at some position x, but I can do this for this value again, which means I would need this value and put it in relation to those two. And so that's the way you go on your whole profile line. It has some benefits regarding stability because implicit time schemes are unconditionally stable. Explicit time steps have stability criteria. We'll talk about this in a second. But this is the big benefit of implicit time discretization. But you will see, because you have several more unknowns which are linked to each other, usually the numerical computation is more demanding. We need to solve a set of linear equations, usually by some iterative procedures, to come up with this consistent formulation. So usually the computational overhead in an implicit time frame is a bit larger than for the explicit one, but you gain the unconditional stability. So how explicitly does this look like? We have the same 1D groundwater flow equation as before. All right. Again, we have the time derivative. We approximate this one exactly the same way. The only change we now do is on the right-hand side, we have also the same grid points involved, so upstream, downstream, and at the current position. But all those ones are now defined at this same future time step, t plus dt. So when I now separate these ones between knowns and unknowns, there's very little I actually know is on the right-hand side. Right? So this is what is known, and all those ones are unknown. But if I formulate this kind of equation for every grid point I have, and I apply boundary conditions for my outermost grid points, then I'm ending up with a set of linear equations which is which is maybe not analytically, but which is solvable in general. Okay, so you see that the computation overhead here is a bit higher, but it is unconditionally stable. So how you do this time discretization? So I used the most simple one, right? Which is called Euler forwards or Euler backwards, depending if you use the implicit or the explicit scheme. But there is a bunch of other methods, right? So another popular one is the so-called leapfrog. It's a higher order scheme because it's a two-step method. So you have an increased accuracy and some other benefits. So it's conservative for a bunch of problems. And then you just say, okay, so this is here, you're not actually considering my current time step, but I'm considering the past time step, and I've set it the future time step in relation to this past time step, right? And now you can think of that there is great numbers of possibilities and variations which you can use, all with its benefits and drawbacks. I won't and can't discuss all of those in here, but it's just for me here, the message is for you to know that there are such kind of methods. And whenever you're using a program and you come across this time discretization scheme, you can look up what the benefits are, what the drawbacks are, and what you might need to consider. So let's compare explicit and implicit scenarios here. I decided again for a very simple 1D problem. I'm injecting warm water on the left and let it flow into an aquifer to the right. However, I assume that the flow velocities of the aquifer is negligible, so I only consider diffusion. Right? It's everything homogeneous isotropic. I keep it as simple as possible, and just want to see how the temperature in the water evolves if there only is diffusion. Okay, and I will solve that numerically with an implicit as well as with an explicit time scheme. And what you can see here is, because it's such a simple problem, I can also have an analytical solution. And I use, for the first simulation, 1.1 times the maximum time step that's given by my stability criteria for the explicit time step. And you see that this explicit simulation has nothing to do with the analytical solution or the implicit solution. You already see that the implicit solution already is quite a good fit to the analytic solution, but the explicit has nothing to do with this. right? And if I decrease my time step further, so I'm coming towards the maximum allowed time step of my stability criteria, we see, okay, now, note the change in x direction. All right, so now this explicit solution is still very oscillating, or oscillation, but at least now the value range is a bit more reasonable. And now if I decrease the maximum time step further, so now I'm at 1.0.1 maximum time step, this one looks way more reasonable. And if I use the stability criteria, I'm seeing this one. So I will do a bit of a recap here. We'll talk about stability in detail a bit later, but what we can already see is an unstable version, unstable model is defined by that existing error, so difference between solution numerically and solution analytically is growing over time. So all those simulations I showed you here, these simulation results, are shown at the exact same time step. And this is by definition still unstable. It still might look quite good, but it just might mean if you run it even further, those divergences you already can observe will grow over time. This solution over here, well, it's not exactly dt max, it's a bit smaller than dt max, is stable, and therefore the error will not grow anymore, right? So don't get fooled by that. This one already looks quite good. Because it's unstable, it will mean that the mistake or the error will grow over time. So to sum it up here a bit, implicit schemes are unconditionally stable. They have a bit of a higher computational demand. Explicit schemes usually require a much smaller time step, but are therefore quick and easy to solve. I will emphasize this a lot over the lecture, but accuracy and stability need to be separated in your head. Okay, I'll define the relation later a bit in sentences, but the accuracy is not depending on if you use an implicit or an explicit scheme, right? If you use a stable explicit scheme, the accuracy will be could be just as good as for the implicit scheme, right? So this is not a criteria for accuracy. Also note, if you ever come to the situation that you have to program yourself, or that you have to choose some kind of time discretization schemes, this is important to consider, because there are schemes which are just unfit to solve the problem you want to have, right? So you can classify, as you hopefully know, partial differential equations into different types: hyperbolic, elliptic, parabolic. And there are schemes which are just unstable for some of those kind of partial differential equations, right? So choosing the correct scheme is a crucial task, and needs to be carefully done. So it's already said, is stability means that the error, so the divergence between numerical and analytical solution, grows over time. So other way around is, if I have a stable solution, my initial error will not grow over time. We can now separate this a bit more. What it means if I have a transient problem, so things are evolving over time, means if I have a bounded solution, or a stable model will produce me a bounded solution, so it means it is within the physical boundaries when my true solution is also bounded. Right? I will talk about this boundedness in a second in this lecture, but already saying here, giving the link to stability, what it means. Also for iterative methods, a stable method converges, so there is actually a solution. I'm narrowing down to the right solution in an usually asymptotic way during iteration. Yeah, because it's approximative, so I'm getting closer and closer and closer. But if I have a stable method, that means my result will converge. And this is maybe one of the most important sentences, I believe, from my point of view, from numerical modeling. It means that just because something is stable, it does not mean that your result is accurate. You can do it the other way around. You can say every unstable model is inaccurate, but not just because it's stable, it will also be accurate, right? You can use an implicit time discretization, which means it is stable by definition. But still, if the time step is very large, your model results can still be very, very inaccurate because there are things coming in there, depending, as I said, on the size of your time step, which is controlled by your spatial resolution, by the physical process you're looking at, by your linearization scheme. Those pacts influence accuracy of your scheme, and that's not just stability. Stability is a point of it, but it's not itself by its own. So this here is a very typical example of an instability and a stable one, right? So again, it's temperature, it just changed a bit. Now it's not moving from left to right. I have a peak signal as an initial condition in the middle, and let this diffuse to left and right. And you will see, okay, this is violating a lot of things. The results are unphysical. I also have a much larger time step than I should be allowed for the explicit time scheme, right? So all those kind of wiggles are always a good indication that the method is unstable. And we will talk about this later here, but you see, okay, the minimum temperature I have in my system is 10 degrees Celsius. So I shouldn't get lower than that one, but I'm getting lower than this one. So, you know, this is violating the boundedness. As I said, the definition comes in a second, but all those are indications for an instability. Sometimes it's easy to see, like here, sometimes it's not as easy to see. Kind of depends on your problem and the time stepping and the time you're looking at. Now I use this term of the maximum allowed time step dt max for the stability in explicit scheme a couple of times. But how did I come up with those kind of maximum time step? And the point is, there are analytical reasons or criteria for stability. And the most common one you will come across is the current frequency Levy criteria, so short CFL, on the so-called current number. So the idea is that the current number is, well, something like a velocity. So it doesn't need to be like the physical flow velocity. It's rather the velocity with which an information is transported, multiplied by the time step divided by the spatial discretization. So you see this here is linking time step and spatial discretization in terms of stability. And this product, or this product that way, should be smaller than one maximum number. And this maximum number is 1. Because if this product is larger than 1, means the information is faster transported than it should be allowed by the characteristics of the system. This sounds a bit abstract. Let's go into more application here. I have the same fine problem as I had it a couple of slides before. So on the groundwater flow, here the explicit formulation, right? So we have this construct here. So this term over here, which is transmissivity and storativity, multiplied by the time step, and here note that it's dx squared because we have a second order derivative. This 2 is also incorporated down here. So, and we all know from the CFL criteria, this all should be smaller than 1. which means we can calculate the maximum time step. So the maximum time step should be smaller than 2 times ds dx squared divided by t. Right, so you can analytically derive this CFI criteria. Don't worry, you usually don't need to do this if you use some kind of commercial program. Because, well, most commercial programs will use implicit time stepping anyway. But if they're not, even then, the time step will be calculated for you to make sure that you fit this criteria, because the maximum allowed time step depends on your discretization scheme. So once you develop it, you know what your criteria will be. But still, of course, you should know a bit what is meant when talking about stability criteria and the CFI criteria. So, and what you see from this CFA criteria, and this is what actually is a message for you as a fractioneer, you say this time step becomes very, very small if either my diffusivity is very large, so the ratio of transmissivity and storativity, or if I get a very small spatial discretization. So my physical parameters, transmissivity, storativity, I can't really change. It is what it is. All right, my system defines it. But of course, the spatial resolution and the temporal resolution are things that depend on my numerical model. So this is something where I have influence as a modeler. And the consequence from this time step criteria is that when I use a smaller spatial discretization, that means I need more cells, which increases my numerical cost. But also, I have a smaller time step due to stability reasons. And again, stability analysis is a very, very wide field in numerical mathematical approaches. Right? You use something like eigenvalue analysis of the forward operator. You can have develop different approaches for instability and stable models depending on the kind of PDE you have. But this is if you want to dig deeper. So for you is someone who wants to apply groundwater models in practical applications. This is the point I want you to consider, because also if you have an implicit model, which means it is unconditionally stable, still your accuracy is linked to your spatial resolution and in some ways linked to the maximum allowed time step of your of this CFA criteria. So many codes use this kind of CFA criteria or some other kind of stability criteria as a value to orient the time step possible for an implicit model. So this is something always to consider. Another value which you as a user should need to check in a model if you do transport processes is the Speculative number. So physically, this is the ratio of advection to diffusion. And the problem is here that if your advection dominates, you need a smaller grid size to adequately resolve those processes. Because so the Speculative number does not depend on the spatial resolution, on the temporal resolution. It purely depends on the spatial resolution. All right. So the proper value here is that the Speculative number should be smaller than 2. This kind of depends on the numerical method used, but remember for your head, because most of the simulations you will do will be finite elements based, and so you have your Speculative number of around smaller than 2 as a value to orient yourself. And this is for transportive processes. especially for the advective diffusive process, which we usually have when we talk about solid transport. Now we're talking a bit about more numerical properties, right? So when we have now spatial and temporal discretization, we can increase or decrease those values, and it tells you something about the quality of your work, or well, not of your work, but of the numerical simulation. And the idea of a convergence is that the smaller you choose your time step and your spatial resolution, so which means physically as closer you come to continuous world, as more the numerical simulation approaches a constant value, right? And it doesn't really say you something about the value it is approaching, right? So that's something where we define in convergence error, right? So it is towards, which is the value of, let's say you're approaching zero, so your analytical solution is zero, and your numerical solution which comes closer and closer and closer to zero, right? But a convergence means is if you decrease time step, if you decrease spacing, you will come closer to this value, at least if your numerical scheme is convergent. Right, so if you consider iterative procedure, which means you're doing a solution over and over again, always using the result of your last step as the initial condition for your next step, so you're coming closer to this approach value, but you will need some kind of termination criteria, because again, numerical simulations are approximations. You won't really hit this approach value usually, but you will come sufficiently small to it, and you will need to define some kind of criteria to terminate your iteration. And then the remaining thing again would be the convergence error, right? The difference to that is the consistency. So the consistency is the difference between the numerical solution and the exact, so the analytical, the truth, yeah, so the exact analytical solution. And the difference between both is what we call the truncation error. And if this truncation error approaches zero, again for small dt's and small dx, so small temporal and spatial resolution, then you're talking about a consistent model. Right. So you could put a bit more simple, in other words, if you decrease dt and dx, your numerical solution approaches the analytical solution. This is what you would call a consistent model. Note the fine difference between consistency and convergence. And then we have conservativity. So I already said at some point, I think for the leapfrog, that it's conservative for some kind of physical processes. What it means is that most partial differential equations we're using are based on the conservation of something. So if you remember the derivation of the groundwater flow equations, it was based on the conservation of mass. So it would be great if our numerical model would also conserve those quantities. And this could be the fluid mass, but it could also be the thermal energy, so the heat, or the mass of solute, right? All of those are based on physical conservation of its quantity. Which means within my system, at all times, I should have the same mass or energy. And a conservative numerical scheme does that, locally as well as globally. So which means, for example, for the temperature example I had in the past, I would not lose any kind of thermal energy, right? Of course, depending on my boundary conditions, I might have a heat flux out of my system. That's okay, that's not what I mean. But I may not numerically lose energy or mass. And you'll notice that this is kind of difficult. And if you remember about the lecture about spatial discretization and finite volumes, right? This is something where you say, well, the benefit of here is its conservativity, because you're transporting mass or energy from one cell to another. So it's automatically conserving, because what's lost in one cell is transferred to another cell. So yeah, numerical schemes, even beneficial, are conservative, but this is not the case for all of those. And then one very nice, because it's so simple to observe or check, which is a property of a numerical solution, is boundedness. Right, I already showed you this example about this example of an unstable simulation, where we said, well, the minimum groundwater temperature in the system is 10 degrees Celsius. And what I actually have is I'm injecting warmer water, or I'm heating up water in the middle. So there is no physical reason that I should have temperatures less than 10 degrees, because I'm not cooling, I'm heating. So temperature should rise, not drop. However, if my solution is not bounded, as there was this unstable simulation, it means it could have values less than my physical boundaries, right? And this temperature one is just one example. You can use that pretty much for a lot of physical problems. Tracer concentration can't be higher than at the injection point, because everything that's happening after is pretty much dilution, but it can never get larger than what we had at the beginning. Or density is limited as temperature is limited. You know, a lot of physical variables and quantities have boundaries, and if it's just means it's non-negative, right? But usually we also have like more constrained boundaries. And yeah, so this is very easy to check. And you will notice if you run especially solute transport processes that this might occur. And you have to examine, is this critical? Is this actually instability, or is it just, you know, numerical noise because it is iterating around zero, and this is also always numerically difficult. So maybe there are some very small, like 10 to the minus 15, 10 to the minus 21 concentrations which are negative, but so small that you can consider it zero, right? So this is, you as a modeler have then the obligation to check if the violation of boundedness is just due to numerical accuracy, or if it really is a physical issue. All right, and I already talked about those kind of wiggles, but if you observe those ones, then you can increase, for example, your spatial resolution, which usually helps to solve these kind of problems, or you otherwise decrease your time step, which is the other possibility to increase accuracy and stability of your problem, right? Boundedness can also be violated by a lack of accuracy, right? Not just stability, but also by a lack of accuracy. As I said, also in an implicit scheme can overshoot your solution, and that means it's still stable because it's implicit, but it's inaccurate. Okay. So this is here a more extreme example of this violated boundedness, right, to make it more clear. And you see very clearly that, well, this is, right, it's unstable, yes, because it's, for me, the most easiest to reproduce violated boundedness. But here now, of course, it's more evident than in the previous example, right? But you see the implicit solution is bounded. Yeah, so maybe there is, I didn't check, some numerical inaccuracy here around the 10 degree line, but it looks, compared to all the others, very accurate and bounded. And then we need to talk about some kind of errors. So this here is like quantitative errors, not user input mistakes you did, but errors in terms of where there is a quantitative difference between your model result and the true solution. And there's something which is very difficult to locate or quantify, is a modeling error. So this means an error that you do by the conception of your model. right? We already learned that every kind of model is an approximation. It's based on assumptions and simplifications we make on the complex solution. The consequence is that if we solve this kind of simplified model exactly, like we're not doing any mistake, we don't have any inaccuracy, we're solving it exactly, still the solution would not be the right representation of the reality. Making an example, when you're modeling groundwater flow, you will assume the density constant. Common approximation works really, really fine. Still, if there is pressure variations, if there are temperature variations, the density is varying along your aquifer. So there is a difference between our model and the reality. This modeling error is probably very, very small, and we really don't care about it because we have other error sources which are way more crucial than that. But still, there is this error. Okay, and of course, this now is a silly example. We can also say like, well, okay, the groundwater flow, we assume it to be horizontal, so we're doing this depth averaging, if you remember in the derivation. So also this is a simplification made. And depending on your problem, this might be a true representation or not. So this is what's meant by the modeling error. Okay, so doesn't mean it needs to matter. It's always there because every model is an approximation and based on simplifications. But there might be scenarios maybe where effects become crucial. So if you are in a hydrothermal system and you have hot water uprising from deeper layers or whatever, then maybe this density effect will be crucial to represent the physical processes because it's based on the density difference between cold and warm water. Right? Then this assumption would be critical and your modeling error would be large and significant. The discretization error results from the use of numerical methods. So because I don't have a continuous wall, I'm in a discretized world in time step as well as in space, there will be inaccuracy, this approximation. And this very much depends on the method you use, on the order of the scheme you're using, so that there are ways how you can influence this one. And modeling is always a balance between the effort and the costs I'm putting in to obtain my solution towards the quality of my solution. Right? So I can get a highly accurate model result, which is really close to reality. But the question is always, what is the questions I want to ask? What is my motivation to do the work? And sometimes this kind of effort isn't worth the benefit of the result, and there is a more simpler model which does just exactly what I need with the accuracy that's totally okay fitting to my problem. So I use the word a lot now, actually defining what is accuracy. Right? And accuracy is a bit of a relative thing. It depends on the motivation and the research task. The idea here is that discretization and convergence errors remain sufficiently small. Whatever is sufficient is, an individual decision. It depends on the problem you want to look at. Modeling errors are out of consideration here because the accuracy of the model doesn't affect the modeling errors. Modeling errors is another category of mistakes, right? Here I have the discretization, the convergence errors, which define the accuracy of my numerical work. It might be that, also mistakes can cancel out, not mistakes, but errors can cancel out each other, right? If I have a coarse mesh, this might be better than a finer mesh for whatever reason. Can be because I need less iterations and my convergence error is so much larger than my discretization error. So, coarser mesh might be better because I have maybe a larger discretization error, but the convergence error is decreasing so much. You see how things influence each other? So this is very difficult to answer in a general sense. But accuracy is one of the, next to stability, one of those crucial numerical parameters that matters for any kind of numerical model. Right, and this is getting a bit more also the difference why we don't include the modeling error into this is because this is the difference between accuracy and validity. Is my model valid? Am I solving the right equations? Did I make the correct approximations for the specific problem I'm looking at? That is a valid model. An accurate model is solving those equations with a sufficient accuracy, right? So this is a bit the difference here in wording. Again, I can't repeat it often enough. Numerical simulations are always approximations, so I always have an accuracy issue. Yeah? But as I said, that's why there this suitable accuracy is put in there. So here you're seeing a bit of dependency of the accuracy on the time step. And I just used implicit and analytical solution. So it is stable, right? We don't need to worry about stability. And you see here, I took as a measure 5 times the stability criteria for an explicit solution. Right? And you might want to see, well, okay, this is half a degree distance. That's fine for me. Good. Maybe you say, well, but I have measurements in the laboratory which give me 0.1 degree accuracy. So this divergence still matters. And then if I decrease the time step further, I will see that the difference between analytical and implicit solution is decreasing. All right, so this is what I said, it's like this maximum possible time step is still kind of an orientation also for an implicit solution with respect to accuracy. Right? So as larger time step is, usually, it's not a general one, but usually it's more inaccurate your numerical simulation results get. How can we quantify and catch those kind of errors? Right? I already named a few very much at the beginning of this course. Right? Verification, validation, benchmark, right, where you compare different numerical codes with each other. All those are possibilities to quantify your discretization error, to get an idea about the accuracy of your model, right? All those kind of things. The difficulty here is that we can have so many different sources for errors. It can be very fundamental in terms of a modeling error, that you just do not solve the applying a proper model for the question you're studying. It can be that you did a mistake in the parameters, that you did wrong units, that you formulated inconsistent boundary or initial conditions. So that this, you know, so many errors which you need to consider and find out, and it's an iterative process to identify, to come up with a good model. Also keep in mind, if you're comparing during validation your numerical results with field results or laboratory results, those are measurements, and every measurement also has a measurement error and a measurement accuracy, right? So, you know, statistical errors of kinds of repeating measurements and that kind of stuff. So this is not the ultimate truth, right? And there's no sense in reducing your modeling error below the level of measurement accuracy. As I said, if I'm in the field and I'm measuring with a thermometer, which gives me like a 1 degree resolution, and I do, you know, statistical error of plus minus another 1 degree Celsius, then there is no sense in pimping my numerical simulation to get an, you know, accuracy of 0.1 degree Celsius. Then with plus minus 1 degree Celsius, I'm good. That's fine. And I can save those kind of numerical efforts to achieve that kind of accuracy. So what I want you to take home from this lecture is know what stability means and how you can detect instability. Getting to know relationships between stability, accuracy, and all the other properties we discussed today. I know what those kind of different properties mean. And you know, again, if someone says, well, my model is consistent or my model is conservative, then that you know, what is he talking about? What does it mean? Is it good? Is it bad? You know, some kind of things. I want you to know that there is something like stability criteria, that you can analytically calculate it, that you can check it, that they are important to validate the quality of your model. And you know, based on the examples, I want you to have an idea of how you can judge violation of those properties, like boundedness, when you conduct your own simulation or when you see simulations of someone else. Thank you.